Thank you very much. Good morning, everybody. Well, let's see if the presentation starts. Oh, maybe it's not. I need to go here. Oh, okay, perfect. Well, I'm Jordi Baylina. I'm the technical lead at Polygon Hermes. In Polygon Hermes, what we are building is a zkEVM fully compatible, opcode compatible rollup. That means that the people that's using this rollup should not see any difference that using Ethereum. The only thing is that this will scale. This will work in a layer 2 instead of working in a layer 1. But this is the main difference against other projects. It's a zk rollup, so we are building a proof that is processing transactions. What means that? That means that we are taking a state, in this case a state root. We have transactions. These transactions are Ethereum transactions, are normal transactions, transactions generated by MetaMask, for example, generated by a normal wallet, standard transactions. And we want to generate a proof that after processing these transactions, we get a new state. So the core of this zkEVM rollup is the prover, is how we prove that those transactions, those transactions here, when we process it, we get this new state. So how we are building this proof? Well, this proof, mainly what we are using here is a technique that mainly what we are building is a set of polynomials. When you hear the word polynomial, you can read it as, you can understand as an array of values. So we are putting an array of values that actually is, that they fulfill some properties. For example, the next value is related with the previous value. So there are some relationships between these values. These are, we call it polynomial identities or polynomial relationships. And if we are able, the idea is to build something that if we are able to build a set of polynomials that fulfill certain rules, then we are proving that these transactions are valid. This seems like difficult because this is a very specific thing, but at the end, the idea is the first step is to think in state machines. State machines is you have some values, then you have some transition functions, some relationship between one state and the next step. You compute the next state, and you have a next state. This is very much how processors work. Processor, at the end, is a state machine. You have some values, maybe the values of the registers, and then there is maybe one register or one point in memory that's the instruction. You execute the instruction, and then you go to the next register. So here you have, what you have is a trace, set of values. Every step is like a clock that's evolving, and then we can build a processor. Actually, this is the map of the basic prover. Here you see we have a processor. Processor is this state machine that's processing instructions. Which instructions? Well, it's a new processor. It's a processor that we define. It's a specific. It works well with this algebraic thing, with these polynomials. But it's a processor. Has registers, has instructions, and it runs very much like an electronic processor. But we have also different pieces. We have a ROM, we have a RAM, we have arithmetic operations, like a kind of a coprocessor that's doing arithmetic operations, that's doing shift operations, that's doing binary operations. Binary here is AND, or short, or less than, more than. You can see all the list of all the different opcodes, and this is part of this processor. This processor is not the EVM. It's just a new processor. It's a processor that's works well with this with the zero knowledge, that we can build this easily, okay? And other more advanced things like we have storage. We have also we have hash functions and so on, okay? And each of these state machines is somehow connected So we have this is a set, the polynomial, so if you want the set of values, we have different relationships, and these processors also connect each other by a set of relationships like this one, okay? This is part of the a language we built, call it PIL. It's a polynomial identity language. Mainly it's just a way of writing all these relationships that the polynomials must fulfill. For anybody interested, I give a couple of talks in the last month talking about polynomial identity language, and it's quite detailed there. So anybody interested there can go to some of my old conference. But at the end, all this language, what it says is just set all these relationships between polynomials. For people, for more advanced zk people, this is very similar, if not the same, that, for example, Halo 2 is doing in the first part. Is building this kind of this array, this table, this set of polynomials with different relationships of polynomials. Okay, so we have all these polynomials. How we build? Of course, we need we call it a synthesizer or an executor. Maybe for the people we are changing the name to synthesizer. At the beginning was executor, but synthesizer because actually what's doing this piece of code is building all these polynomials. We start from a set of transactions. We start from a full state of Ethereum, and then we compute all these polynomials. Actually, we are executing a program in this processor that's emulating these transactions in Ethereum and building all these polynomials. Okay, these polynomials have the resulting this array. We have also the PIL. This PIL is all these relationships that all these polynomials fulfill. At this point, we could check it. You know, is this PIL matches this? We can manually check it, and actually we have a tool to do that. We can check, but we don't want to check it here. Actually, we want is to generate a proof that we have some polynomials that fulfill this. Actually, that these public inputs are correct. Okay, so we need to generate a zero-knowledge proof out of these polynomials. How we do this? Well, actually, in our case, we are using a Stark. We generate a Stark. This is generated quite automatically. Until here is building this process. But at this point, with the PIL and with the polynomials, we can generate this, this is a Stark. At the end, it's a proof that's a Stark. The problem of this Stark is that's quite big. You know, the Stark, if you want to, at this point, we could finish here. We can put this Stark and put it on chain, but then the Stark, it's expensive to validate on chain. So we need to do it better. Also, there is another trick that we are start doing now, is that these polynomials, we are using a small field. This is something that we changed in the last versions. We were convinced by the colleagues of Polygon 0 that they have a talk later, and using a Stark with this small field is a 64 bits field. Then the generation of the proof is much faster. We increase at least even more than one order of magnitude the speed of this prover. Okay, so we have this Stark, but this Stark is still big, and the quantity of transactions that we can prove here, well, is not, depending on how big those polynomials are, but it's not that much. So we need to do something else. Actually, what we are doing is we are aggregating many of these proofs. So here we have we have here in the bottom many of these proof. We can generate a kind of a tree. We can generate here a kind of a tree of proofs. This is a proof that proves many proofs, so we generate a proof. In the top, we have like a single Stark that proves all these proofs here, and then we prove this Stark with a Groth 16 or a Plonk. So actually, this is a circuit, a Groth 16 or a Plonk circuit. Actually, it's a circuit written in Circom. It's automatically generated from the PIL, but written in Circom that actually proves all this structure. The cool thing here is that we can, in this last step, we can personalize, we can generate the Stark in the way that we minimize the number of constraints that we need in the Groth 16. And the cool thing here is that when we verify this in the Ethereum blockchain, the cost is the verification of a Groth 16, which is about 300K gas, which is much, much, much less than verifying a Stark proof. And this structure, this recursive structure, give us all the scalability, because you can build all these proofs in parallel, and then aggregating them is quite cheap. So this is very much a little the structure that we are building. But of course, this is a processor. Okay, here we have just a single processor. But what this processor is running? Actually, it's running a program that's stored in the ROM. We call it a ROM, but at the end it's a polynomial or a set of polynomials. That's the instructions, and they are hard-coded. They are specific. It's like part of the, like if it was a smart contract, we cannot modify that. Is the when you start this process, you need to run this ROM. And this ROM is a program written in assembly. It's not a normal assembly. It's an assembly made for this processor. And actually, what this program does, well, this program emulates Ethereum. It takes the transactions, it parses the RLP, it takes it verifies the signature, it checks the gas, it removes the balances. If it's to deploy a smart contract, it deploys a smart contract, it hashes the program, it put it in the storage. Actually, it does one thing after the other. Here is just 2 snippets to show you how it looks like. In the left side, you can see, for example, the beginning of the RLP, how we are parsing the transactions. And in the right side, we see an example of a couple of opcodes in Ethereum. But opcodes in Ethereum at the end are procedures of this assembly. So somehow we are rebuilding, we are creating a new Ethereum. So we are emulating Ethereum on top of this processor. Okay. Of course, the node is the prover is not the only thing. Here there are other pieces that I want to mention here just to finish my presentation that are important. One part is of course the node. We need somehow to accept transactions. There is a transaction pool. We need to synchronize. We need to keep a database of the state. So there is an important part. That's the node. This part is for the people that comes from optimistic rollups. Is very similar in the sense, because at the end it's keeping the track of the state and so on. And then we have the different smart contracts. For the smart contracts, I want to mention, for example, how we select the validator. Here we are using an approach that's very, very, very similar to the one that was presented yesterday for the Arbitrum people, but it's quite similar. The idea is to maintain on-chain 2 states, one that's implicit and the other is explicit. Here we have a set of sequencers that, well, actually it's not a set. Anybody can be a sequencer, and the idea is that anybody can put transactions on-chain. So, and at the moment that those transactions are put on-chain, they are already sequenced. And so they are already final if you want. The state is not is implicitly known, so anybody can calculate the state, but this state is not on-chain. And what makes this state explicit is the prover. So there is later on. So once these transactions are here, it's going to be somebody that's going to validate those transactions. In the case of the optimistic rollup, you have to wait maybe 1 week so that the people that nobody challenge that those transactions are valid. In our case, the idea is that a prover can validate and put this implicit state in maybe in 1 hour or in 10 minutes or in 15 minutes. So you can withdraw and you can, for example, transfer these funds to another chain faster. You see, this is the big difference. And the other difference also is, well, in this case, in the proposal that we made of proof of efficiency is that it's pure decentralized in the sense that anybody can be a sequencer. There is no single sequencer. Actually, it's not a sequencer. The sequencer is Ethereum, so when somebody puts the transactions there, then they get sequenced. Yeah, if instead of allowing anybody to be a sequencer, you define a centralized sequencer, and only this guy put a sequencer, then we have more or less what we had yesterday, what we saw yesterday with Arbitrum. But the idea is very much, the concepts are very much the same, and here the balances are the same. Of course, you can have, instead of having a centralized sequencer, you can put maybe another consensus layer with different properties. All the things apply exactly the same way that on an optimistic rollup. And the other part is also the bridging, how we transfer value, how we transfer tokens, NFTs, or any value from, how we pass messages even from layer 1 to layer 2 and from layer 2 to layer 1. This is where keeping also a different smart contract. That's we have a different smart contract where you store the funds in the mainnet, and then we keep 2 trees, one in the mainnet and the other in the rollup. And the idea is that the root of this tree, that's always aggregate tree, is the tree that you only can aggregate, is transferred from layer to layer, from layer 1 to layer 2, and from layer 2 to layer 1. Every time that the proof is generated. Every time that the proof is generated, this tree is synchronized, but it's just a single hash. It's just the top of the tree. It just synchronizes with the global tree. The global tree is synchronizes with the main tree. And with this, in this tree, you can add the exits, and then you can transfer from one side to the other. This approach can be used for not only for a single rollup, can be used in many rollups. Of course, here there are some security difficulties, which rollups and how you select which rollups here, and there are things to do. But at least here, just take it as we use it as a standard way of transferring value between layer 1 and layer 2, and from layer 2 to layer 1, like a normal exit. And finally, the status of the project. At this point, we have, I would say, 95% of the state machines developed. We have the first version of the assembly generated. We are missing a couple of state machines that are the easiest one, but we just left them for the end. We need to put everything together, and I hope that in, I don't know, 2, 3, 4 months, we can launch a public testnet. We are in this phase, that things may happen. When you put all the things together, you always find things, and do not take it as a commitment, of course. We are just working as hard as we can, and we are going forward, but we should take, at this point, it's just a matter of developing. It's still a lot of work. Testing all this is going to be like the next phase. Auditing, there's a lot of code and a lot of things that needs to be audited, and putting this in production is going to be an important effort too. But first step is testnet, and I think we are quite close to be there. And yeah, that's very much my presentation. I think I'm in time, so if you have questions, that would be great.
Thank you very much. We've got the catch box, and yeah, just watch your laptop.
Hi. Can you talk about some of the downsides of proof of donation and why Hermes decided to go from proof of donation to proof of efficiency?
Yeah, proof of donation, the main problem is that in proof of donation for the people is there was an auction. The idea is that somebody had to, well, you are bidding for a slot, and anybody can bid for a slot, and then during that slot, you can generate as many proofs as you want. The big problem is that we found here is that, especially in the bootstrapping process, for example, it was very easy to attack the network. Somebody can buy very cheap, an important and a lot of time in that place. So here we had to design some, let's say, tricks to defend, especially in the bootstrap part. Also, even if it's not attack, if in the proof of donation, if one operator do not operator is not working, has some problems, then it stops the network for 10 minutes in the case of push donation. That was another problem. Also, the finality of the transactions. With this model, you don't need to wait to a proof to be generated. We are applying a kind of a mix between it's the idea of the optimistic rollup, but with the zk rollup. So once the transaction is put in the on-chain, you know that that transaction is final, and then the proof can be generated later. You are not that much in a hurry, so this is it's much superior. This protocol is much simple, so it's the evolutions, we got the experience, and also, for example, monitoring for the bidding. How much you have to pay for the bid. Well, you need to do predictions in the future. This is also not easy for operators to calculate or to manage. Also, for proof of donation, you need a minimum. If you have a few transactions and it's not worthy, maybe nobody's going to bid, and then you need to have a kind of a bootstrap operator. So there were some issues, most of them related to this bootstrapping part. But this process, so this way is much simple, much clean, and yeah, that's much better.
Anyone else? Yeah, we've got the question behind.
Oh,
almost. Sorry about that.
On one of your slides, you showed that you first generate a Stark proof, then aggregated Stark proof, and then Plonk proof that proves the recursive Stark. Why make a Plonk proof that proves the recursive Stark when you can just make a recursive Plonk proof from the beginning?
Because Starks is generated much faster.
Okay.
Any more? We've got time for one more question. Or two.
Like in this slide, what do you prove with the Plonk there? Like you have this tree of Starks, and then?
Yeah, we are, let's see if I say in the right way. We are proving that we have a proof that proves many proofs, that those proofs each of the proofs that I want to prove. Something like that.
Easy.
But it's proven. It's proven, that's the goal. A proof is a proof.
I have a question. Who's going to audit that?
That's it. Any more questions?
There's one over there at the back.
Hello. If you have Starks in the middle, does that mean you can't do privacy at any point, or is that on the roadmap?
At this point, yeah, privacy is an important issue. We have absolutely in mind. The truth is that at this point we are not focusing the privacy. At this point we are focusing generating the proof without caring too much about privacy. The first goal is to scale in our case, but this structure, when at the moment that you have recursion, adding privacy should be easier, or at least a step forward to go in that direction. We will go there. We need privacy. We are for privacy, but we need to do, I think it's better approach to solve problems one by one, not trying to solve many problems at the same time. We are focused at this point in having full rollup, proving Ethereum transactions. The challenge is important. Having opcode compatible Ethereum transactions is a challenge, an important challenge. And with that working, we will continue working with privacy. And this structure is very good for that.
I guess what I meant, sorry, is like if your EVM contract implements cryptographic primitives that are needed for privacy, is it compatible with
Yeah, actually, for example, just to mention something, when we start this project, one of the things that we first remove from the question, it says, we are not going to implement this, or this is, maybe it's not going to be, well, this is probably not going to be possible, is, for example, this EVM will not have pairings. Okay? That was the beginning. Okay? At this point, we learn a lot about, especially for verifying the CDSA circuit. So we know now how to do cross-prime field operations quite cheap in the Stark. And this probably in the first version we will not have pairings, but now definitively we see that's perfectly possible to implement pairings in the EVM in state DOS. It's perfectly possible, and it's just, well, it's work, but it's doable. And if we have pairings, we can have, for example, Tornado Cache running on L2, and we can have any privacy application running on layer 2. So this is also this is important, and it's another way of getting the privacy. But I think you can do here with this structure. You can do many things in there. I'm not like a super expert in the Starks, and doing a Stark with privacy requires some extra. You need to pay attention, and you require some extra details that you need to take in account. But it's perfectly doable.
Jordi, we have to take the rest of the discussion outside. We ran out of time. Thank you very much again. And, thank you for kicking the day off.